Hello everyone, this is Abhinaya. So this video is a part of my assignment for the course Computer Organization and Architecture. So in this video, I'll be explaining the analysis of microprocessing element, and the microprocessing element that I have chosen is AT-Tiny13A, which is from the Atmel family. So in this video, we'll be discussing in detail about this microprocessing element. So let's go. So in the first question, they have asked the block diagram of the microprocessor, which I have taken as AT-Tiny13A. So this is the basic block diagram of that microprocessing element. As you can see, it has an 8-bit data bus and it has stack pointer, program counter, the memory unit, program flash, and also the general purpose registers. And in this side, you can see the types of register and the types of timer which is present in this microprocessing element. And if you see down here, you can see the analog comparator and the data register ports, port A and port B. So this is the first block diagram, and you can see the pin configuration, which is like a part of the internal diagram of each and every block. So this is the pin configuration, and this is the block diagram of the internal system, which has the control unit, and it also has the clock multiplexer and the watchdog oscillator. You can see this as an internal system. And this is the block diagram of the comparator, and this is the block diagram of the counter unit. So in the second question, they have asked the instruction set of the microprocessing element based on addressing modes and operation. So it includes like clock cycle, mission cycle, and memory required flags and all. So you can see this is the instruction set of the microprocessing element. So this is actually taken from the datasheet of the microprocessing element, which is available in the internet. And in the third question, they have asked the microprocessing element architecture. So basically, this microprocessing element has the RISC architecture. So RISC architecture are simple and are free fixed size. So each RISC instruction engages a single memory word. So RISC instructions operate on process registers only. The instruction that have arithmetic and logic operations should have their operand either in the processor register or it should be given directly in the instruction. Like in both the instruction below, we have the operands in register. So you can see here, so this is an example of it. And you can see the basic flowchart of the RISC architecture. So this is the main memory. So this is the hardware control unit, and this is the data path, and this is the instruction cache, and this is the data cache. So the process works as per the flowchart. And you can see this is the memory space of the architecture. So basically it has the SRAM data memory. So the lower 160 data memory location addresses both the register file and the input and output memory and the internal data SRAM as well. So the first 32 location addresses the register file, and the next 64 locations addresses the standard input and output memory, and the last 64 locations address the internal data SRAM. So there are 5 different addressing modes for this microprocessing element. So that is direct, indirect with displacement, indirect, and indirect with pre-decrement, and indirect with post-increment. So we'll be seeing about it. So coming to the status register, it is like global interrupt enable. The global interrupt enable bit must be fed for the interrupts to be enabled. And you can see similar to that, we have bit 6, bit 5, bit 4, bit 3v, bit 2n, and bit 1. So these are the flags: carry flag, zero flag, negative flag, and we also have 2's complement over flag, half carry flag, and bit copy storage. So these are the carry flags which we saw in the status register. And this is the addressing mode. So the addressing modes are direct, indirect with displacement, indirect with post increment, and indirect with pre-decrement. So this is the general representation of a direct addressing mode, and this is the general representation of an indirect with displacement. Similarly, with indirect with pre-decrement, indirect with post increment, and this is a representation of the indirect addressing. So in the fourth question, they have asked us to correlate the microprocessing element that I have chosen with the architecture discussed in our curriculum, that is from module 1 and module 2. So in our lectures and modules, we have discussed about both RISC and CISC architecture, and basically this microprocessing element that I have chosen is based on RISC architecture. So in the Harvard architecture that we have discussed is the computer architecture that contains separate storage and separate buses like a single path for instruction and data. So the another architecture has we have discussed that the modern computers are based on a stored program concept introduced by John von Neumann. So this is a von Neumann architecture. In this stored program concept, programs and data are stored in a separate storage unit called memories, and they are treated the same. So you can see this is the block diagram of the architecture. So a reduced instruction set computer, that is the full form of RISC, is a type of or category of the process or instruction set architecture, ISA. So in the fifth question, they have asked to elaborate the register organization of microprocessing element. So the general purpose register file, we can see that we have four kinds of general purpose register file. The first one is one 8-bit output operand and one 8-bit result input. Similarly, we have two 8-bit output, and we have two 8-bit output operands with one 16-bit result input and one 8-bit result input. So there are two differences here. Only the input varies. So there is one 16-bit output operand and one 16 result input. So we can also see we have three kind of register: the X register, Y register, and Z register. And this is the basic representation of it. So coming to the stack pointer, so basically the stack is mainly used for storing temporary data, for storing local variable, for storing return addresses after interrupts and subroutine calls. So the stack pointer register always points to the top of the stack. So there's actually an important point to note that the stack is implemented as going from higher memory location to lower memory locations. So this is a representation of the stack pointer, you can see. And in their sixth question, they have asked to explain the type of algorithm used for signed and unsigned calculation. So in this slide, we will be seeing about the signed multiplication and its algorithm as well. So the algorithm for signed 8 into 8 multiplication is as follows. So you can see there are 8 steps for this signed multiplication. So initially we need to clear the result of the high byte and carry, and we need to load the loop counter with 8. So if carried, previous bit 0 of multiplier set, add multiplicand to result high byte. And the fourth step is if current bit 0 of a multiplier set, we need to subtract the multiplicand from the result high byte. The fifth is we need to shift the right result high byte into the result low byte, which can also be the multiplier. And in the sixth step is the shift right result low byte, which is also a multiplier. The seventh one is decrementing the loop counter. And the eighth one is if loop counter is not 0, we need to go back to the third step and we need to repeat the all process again. So this is the basic flowchart of the this process. And in the unsigned multiplication, it is similar as that. We have the same 8 steps. And this is also the flowchart for the unsigned multiplication. So in the seventh question, they have asked to find what type of control logic unit, and we need to correlate its performance with the type of control unit that we have discussed in the module 3 of our curriculum. So in module 3, we have discussed about the microprogramming control unit, and the control signals associated with the operations are stored with operations that are stored in special memory units, and it is accessible by the programmer as control words. So basically, coming to the hardware control unit, we can see that this control hardware can be viewed as a state machine that changes from one state to another in each and every clock cycle, depending on the contents of the instruction register and the condition codes and the external inputs as well. So the outputs of the state machine are the control signals, and the sequence of the operation carried out by the machine is determined by the wiring of the logic elements, and hence it is named as hardware. And you can see this is the basic representation of the hardware control unit. And basically the RISC architecture is based on a hardware control unit. So basically the microprocessing element is actually has the control unit, which is hardwired control unit. In the eighth question, they have asked to explain the memory management system and the processing element. So in this thing, we'll be seeing the addressing capabilities, memory mapping technique, and also the advantages of the memory design and management techniques over the concepts given in the module 4 of our computer organization and architecture syllabus. So you can see the mapping technique is the self-programming the flash. So this is one of the mapping techniques. So you can see that like before programming a page with the data stored in the temporary page buffer, the page must be actually erased. So the temporary page buffer is filled one word at a time using SPM, and the buffer can be filled either before the page erase command or between a page erase and a page write operation. And coming to the addressing capabilities, you can see that it has the capability of addressing the flash during self programming. So since the flash is an organized in pages, the program counter can be treated as having two different sections. So one section will be consisting of the least significant bits, that is like addressing the words within a page, while the most significant bits are addressing the pages. So this is shown in the below figure that is here. So you can see that the note that the page erase and the page write operations are addressed independently as shown in the figure. So therefore it is like of major importance that the software addresses the same page in the both page erase and the page write operation. So in the ninth question, we can they have asked to elaborate the pipeline and parallel processing capabilities of the unit and its hazard management technique. So you can see that the pipelining introduces latches on the data path, thus reducing the critical path. So this basically allows the higher clock frequencies or sampling rates to be used in the circuit. So in a parallel processing, logic units are duplicated and multiple outputs are computed in parallel. So you can see this the parallel instruction that fetches an instruction and the instruction gets executed. So this section describes the general access timing concept for instruction execution. The AVR CPU is actually driven by the CPU clock, and the CPU directly is generated from the selected clock source for the chip. So this is the basic pipelining concept to obtain up to one MIPS per megahertz with the corresponding unique results for functions per cost and functions per clock or functions per power unit. So here the the above diagram shows the internal timing concept for the register file. So in a single clock cycle, an ALU operation using two register operands is executed and the result is stored back to the destination register. So you can see this is a single cycle ALU operation. So now coming to the hazards. So the structural hazard is you can see that the hardware cannot support certain combinations of instructions, that is like two instructions in the pipeline require the same resource, like so these kind of instructions the structural hazard cannot like the hardware cannot support it. So this coming to the second hazard, it is a data hazard. So instruction depends on result of the prior instruction still in the pipeline, so it doesn't react to the like or what on the commands which has been given at that instant. So in the third thing, third hazard is the control hazard, which is caused by delay between the fetching of instruction and decision about changes in the control flow, that is the branches and the jumps. So in the 10th question, which is the final one, they have asked to find whether the processor level parallelism is available in the element that I've selected, and we need to illustrate the cache coherence and protocol used for handling memory, that is hit or miss. So yes, the processor level parallelism is available in the microprocessor that I have chosen. So parallelism comes in two general forms, that is the instruction level parallelism and the processor level parallelism. So parallelism is exploited within individual instructions to get more instructions out of the mission. So fetching of instructions from memory is a major bottleneck in instruction execution speed. So below you can find the types. So you can see the here in this processing element, here we have used the instruction level parallelism. So this is the basic flowchart of the instruction level parallelism. So first the memory is fetch, like the fetch instruction from the memory. Then after that it decodes the instruction and calculates the effective address. After that it comes to the branch. So it can either go directly to the PC and it can like go to the empty pipe, or else it can go, if there's a branch, it will go like this, and if there's no branch, it can go to the segment tree. So it will fetch the operand from the memory and it will execute the instruction as segment 4, and it will enter into the interrupt. So if there's an interrupt, it will go to the interrupt handling and then go to update PC, then go to the empty pipe. If no, then again it goes to the instruction, like it goes to fetch the instruction from the memory, and the same process continues until it gets an interrupt. So you can see the types of parallelism. So basically there is data parallelism, task parallelism, bit level parallelism, and instruction level parallelism. But you can see that in this microprocessing element, there is the instruction level parallelism, which means the simultaneous execution of multiple instructions from a program. As you can see in this flowchart, there are three types of programs which is operating simultaneously at a time. So, while pipelining is form of ILP, we must exploit to achieve a parallel execution of the instruction in the instruction stream. So, you can see that clearly. You can see that in 80 tiny 13A, the instruction level parallelism takes place. So, in the multiprocessor cache coherence, so symmetric shared memory machines usually support the caching of both shared and private data. And in cache coherence protocols, there are two types of thing, that is directory based and Snoop based. So in directory based, the sharing status of the block of a physical memory is kept in just in one location. So it is called directory based. And in Snoop based, we can see that the caches are always accessible via some broadcast medium. Either it can be a bus or a switch, and all the cache controller monitors or snoop on the medium to determine whether they have a copy of a block that is requested on a bus or a switch access. So it is called as snoop based. So this is the flow chart of it. So this is the analysis of the microprocessing element that I've taken. I hope you understand and like it. Thank you.